Hello guys. So first of all, how do we use these new Christmas hats? Oops. Nope, doesn't work. Oh, whatever. If someone can look at that and tell me, I'm curious. For those who follow the series of about the X1 educational operating system, kernel, really, I tried to do that with Metal Snake, but he's not answering, so I suppose something has happened for him, and he has to deal with it. Like maybe he doesn't have internet or something. I don't know. So again, it will just be me this time, and I hope the music will not make the video mute, filtered. If it is, well, that would be a shame, but it's much better with music, at least for me. Otherwise, the stream is just... something's missing without music. Hello, Michael C. Long time no see. Well, long time, not really, but 2 weeks maybe? I don't remember. Okay, so last time, which was actually Wednesday, only 2 days ago, I worked on multithreading, and I reached a point where I can run multiple threads, which is great, right? So this is the code I have, where I create 2 threads that run the same function with different names, and each of those threads prints its name and then yields the processor to anything else. So the result is a bit uncomfortable, as you can see, because of this. So I can stop execution, and we can see that the threads run one after the other, and they have to, because nothing preempts the threads. So currently it's only cooperative scheduling. Now, one thing I like to do before making any other kind of progress is handle this situation. So instead of printing the name continuously, let's just print it once. And so now the threads will only call thread yield. Thread yield is here. And it calls run queue schedule, it disables interrupts, etc., etc. So there it is. I've changed the code slightly. So this is what I have. Now those threads, and maybe we can see them here. Let's take a look. Yeah, okay, I have a single processor, that's right, so it's not really useful. But basically those threads consume 100% of the processor. Not each of them, obviously, but both of them. The processor is never idle. Now, if I let it like this, it's okay, but if I add something like interrupts, it's not. So first, if I type something, you can see that nothing occurs, and the reason why it doesn't occur is because interrupts and preemption are still disabled at this point. And that's because last time I forgot to make the thread main function enable them. So here I assert that interrupts are disabled, which is expected. This is part of the preempted state. And I assert that the level of preemption is strictly 1. Again, that's part of the the preempted state. So I'm going to enable interrupts, and I'm going to enable preemption. And this should be better. So one thing though, before I do that, it's not normal that I can yield the processor here while preemption is disabled. So this is a problem, and I want to fix that right away. And so to fix that, what I should do here is assert that preemption is enabled when calling this function. Or what I could do is actually move that into the yield function, and I think I'm going to do it that way. Because I expect the scheduling function to be called from other functions. And those functions may have interrupts or preemption disabled already. So I'm moving synchronization to yield directly. Okay, so this is a critical section that disables both interrupts and preemption. And here I want to make sure that the level of preemption actually, so prev, preempt level is strictly 1, and I want to make sure that interrupts are disabled. This is the state expected when scheduling. No interrupts, no preemption, but the preemption level must be strictly 1, so that when we get out of the function and enable preemption again, it becomes 0. Okay. And now normally I should have an assertion, because that's not the case. And I do get the assertion. Great. So now let's fix thread main, so that we actually call the thread function with interrupts enabled and preemption enabled too. So first thing, there will be no assertion normally, okay. And second thing, interrupts are enabled, which means that if I type something, it prints. Okay. Now, I'm almost certain because yeah, I remember it now. Here in the CPU, I think it's assembly. Yeah. CPU interrupt common. That's it. So this thing here is the common interrupt handler. This is where all the interrupt handlers, the very low level interrupt handlers, so the interrupt service routines, jump to. And this thing calls interrupt main. And actually the only things that are saved on the stack are things that are pushed by the processor itself. So let's take a look at that. I have it already. Okay, this is the big combined volumes of the Intel architecture. And I'm looking at interrupt and exception handling, and I want to know how to handle them. Okay. So what I'm looking at is the stack on interrupt. When an interrupt occurs, this is what the processor does. The processor pushes those things on the stack. And so the stack pointer is there after transfer to the handler. So you can see that this is not much. This is basically this is almost nothing. Which means that all the core registers are unmodified. So, well, especially they're not saved. So when you call your handler here, your handler may use core registers, it's very likely, and so when you return from interrupt, those core registers will not be restored to their previous value, which will probably cause, corruptions, bugs. So I expect a bug here because of that. And it should be easy to reproduce. Yeah, okay, I have it now. So one reason I can type it so many times before it occurs is because of this. I disable interrupts and I restore them here, which means that most of the code here occurs with interrupts disabled, which is why it's less likely than it should be otherwise that a corruption would occur. So I want to fix that first of all. And in order to fix that, I need to save everything that might be used by a thread. which includes all core registers and segment registers as well. And I'm going to shamelessly copy a macro, well, two macros actually, that I wrote for another project, because I like saving my time. Okay, which are these ones? Okay, I'm gonna add them here, rename them. Don't load segment registers. Okay, so one thing I can assume is that the processor, well, sorry, the compiler is never going to change a segment register. Never. That's part of the ABI. The compiler assumes that segment registers already have a value, a valid value, and that it can't know what segments are used and what values to assign to the segment registers. So the compiler is never going to generate by itself instructions to change them. So I just don't load them, which means I don't even need to save them here. Okay, so I push EDI, ESI, EBP, EDX, ECX, EBX, EAX. Okay, these are the core registers. A to D, then the frame pointer, and then EDI, ESI. So the source and destination indexes. Okay, here they are restored, so in the reverse order, because it's a stack, so last in, first out. Okay, skip segment registers, vector, and error. Not sure why. I mean, skip segment registers, yes, but vector and error? I don't really get it. Let me check again the other file. Oh, yeah, okay, right. That's because there is some tricky stack manipulation here, okay, that we don't have, so I probably don't need to do that at all. Okay, here we have a small subtlety. We have some exceptions with an error code, which is pushed automatically by the processor here, error code. And some of them don't have an error code. So, in order to have the same stack frame, what I do is that I'll always push the, I push a dummy error code here, but that's because I want a fixed trap frame. And I don't need that here, because we don't pass those registers to the C code so that the C code may, for example, dump them in case of an unhandled fault. So because I don't need a fixed structure with fixed offsets, I can just ignore the... Well, can I ignore the error code? I don't think I can, because... Yeah, I don't think I can because on return, and that's why, yeah, okay, I understand now. That's why I have those. This thing here is going to be called on return from this. So it's basically that. It's this thing here, but encoded in the macro. I think it's ugly in the macro. It makes it not symmetric with the store one. Probably change that in the other kernel too. So I have to push a dummy error code, because when I get to this point, I don't know if I was called by this or this macro. So I have to skip that, the vector and the error. Okay. I can't have two values here. I need to have one that works for both. So I push a dummy error code here. I know there is one here, and 8, which is 4 times 2, so two words, works for all cases. Okay, so also it's weird because some files I use a different indentation here, if I remember correctly. Yes, I use 2 spaces, which is probably better than just 1. So let's change this as well. Okay, that's all. So CPU interrupt store registers, and then here we have CPU interrupt load registers. So this saves the state of the processor, of the thread actually, on the stack. Keep in mind that when a thread is interrupted, the interrupt handler runs on the stack of the thread. We don't have a stack switch here. We keep using the same stack. The stack pointer is just incremented by the amount of space needed for these, and obviously those. But we keep using the same stack. So we save the state of the thread on its own stack. Then we call the interrupt handler here, the main entry point for interrupt handlers, then we restore them. And so we skip here, we skip those things. And then we return from interrupt. And normally when we return from interrupt like this, all the state of the thread is the same. Except obviously if the interrupt handler changes something, but that's not the case here. And it should not, because we don't handle thread-specific exceptions like page faults, it should never be the case in the kernel, in this kernel. Okay, RQ, so we have something that fails here, lookup interrupt handler, fail, okay. So apparently we have an argument that becomes wrong now. IRQ less than size of interrupt handlers, okay. I'm going to take a look at the value, because it might just be plain corruption or an invalid stack address. Okay, yeah, I'm going to disable optimizations. Optimizations make debugging quite difficult. We can finally, yes, indeed. A couple of weeks, I think, yeah. Xmas hat, yes, Xmas hat. So, how do you use that? If you can tell me. Obi Skywalker. Alright, let's see. Lookup interrupt handler assertion. So the vector is 514. Yeah, no, that can't work. So what did I mess up here? I don't have to push like these. These are useless. Push vector, okay. That's useless too, that too, that too. Actually that's not, no, that's not useless, because the assembler can infer the size of the operation based on the name of the register, but it can't do that with immediate values like 0. Hello ABDCW. I don't know how to pronounce that any other way. So what's happening here? Okay, what's happening here is that we are pushing stuff after the vector. So the way arguments are passed on x86 32 bits is completely through the stack. So obviously if I change the stack, I change the arguments. So now this thing uses the last register, so AAX, as its argument. And obviously that can't work. So what we could do... Yeah, we could have a trap frame. Okay, let's make a trap frame. Okay, so the structure I'm going to write must completely match what is passed on the stack here. Also, I have a question about alignment. Because here, when the interrupt occurs, so let's take this diagram here. When an interrupt occurs, I don't know about the stack here before transfer to the handler. So if the stack pointer is not aligned, which is possible, I don't know, pushing a certain number of words will keep the stack pointer unaligned. So are there alignment constraints? I can only see that for now. It's only about privileges. That's actually a good question that I may have wondered about that earlier, but now I can't remember at all. Let's take a look. Actually, I might just want to check the AMD documentation. Let's see. So system programming is volume 2. Exception and interrupts. Legacy protected mode. Control transfers, okay. Locating the interrupt handler, so that should be, well, it's already done. This is only about privilege checks too. It doesn't look like the stack is aligned. So the x86 architecture supports unaligned accesses, which means that it will work anyway, but the ABI has requirements about how the stack must be aligned, so I'm a bit surprised about that. Let's ask Google. No, that's not it. So apparently the processor doesn't do anything itself, so that's a bit annoying. So what I imagine is that what we push on the stack here doesn't need to be aligned. It's okay if it's unaligned, because it's not data that is going to be accessed a lot. And then what I should do is that before calling this, I should realign the stack. And then here we should restore it to a value that points to those registers here. Well, actually, this thing pops. Okay. So yeah, right after the function, right before loading registers from the stack, we should realign it so that the pops here correctly work. Okay, so I don't really care about alignment. I don't need the structure to be packed. I can directly write my frame. So, what is on my frame and how to build something like this? I need two things. I need to know what the processor pushes, and then I need to know what I push after that. Everything is 32 bits, so I can just use uint32t for my members. The stack grows downwards, which means that the lowest address, which is the first member, is actually going to be the last one that is pushed. And so the last one which is pushed is EDI. Then ESI, EBP, DX, etc. Okay, then we're here. So error code. EIP, the code segment. The code segment is normally 16 bits, but I think it's pushed on 32 bits. I hope so. Same privilege level, the processor saves the current state on the current stack, push the current stack after the EIP value. Okay. Well, the width is the same, so I suppose it's 32 bits. Then we have E flags, and that should be it. So in C, like when you use packed, which actually is a macro to this thing here. So it's an attribute, compiler-specific attribute, which is named packed. This basically means that if your structure has holes or padding, these will be removed. But here we don't need it because we can rely on what the C language specifies, which is basically that all your members must have the correct alignment. So the structure is laid out in a way that makes all members automatically aligned. If the beginning of the structure is correctly aligned as well, that is. And since all the members have the same type, there will be no hole, there will be no padding. Okay. So let's take a look at the assembly code one more time. Okay, the stack pointer. So that's important. When we call this function, what we have on the stack is just the last register which was pushed. It's not the frame itself. So I would assume that in the other code in 32 bits, we should push the stack pointer itself, normally. Yeah, so it's this thing. Stack tracing, right. EBX should be saved here. Yeah, save frame. So we move the stack pointer to EBX, we push it on the stack, and then it's used again here. We push it again here. So that's the push that is needed. In 64 bits it's not needed, we can directly put that in the register. Oh, that's right. Yeah, I don't have many comments. Okay. When I say trap frame, exception frame, interrupt frame, it's the same thing. I basically use the words interrupt, exception, or trap interchangeably. Okay, so now I should have it. I can use printf to debug that. Let's see. Oh, I don't have a vector. Yeah, that's right. I didn't correctly look at the frame here, and I forgot the error. Well, no, actually, I didn't forget the error, but I forgot the vector. So the vector is pushed after the error, which means that it's higher in memory. Okay, conflicting types. That's right. Vector 0, yeah, that's not okay. Let's take a look at the trap frame. Oh, the frame points to the heap. It's not. Well, actually, yes, it's normal. The stack is allocated after the heap, so that's okay. The code segment is indeed 8, I think. E flags, this looks like a correct value, but the vector being 0, that's not okay. The vector should be 36, so I apparently inverted them, really. The vector is at a higher address. Oh yes, it's pushed after and it goes downwards, that's right. We have... Oh, so 13 is a general protection fault. Which means that this one is correctly handled, but inside, well, correctly handled, we correctly reach this thing here, this printf, but then something else occurs that causes a general protection fault. And we don't have a handler yet. Currently, I only have interrupt handlers. I don't have a handler for the general protection fault here. Yeah. Okay. So I need to understand why I have such a fault. I should have 2 frames now. Well, I should have the last frame, the frame for that exception. This is the instruction that fails. So let's take a look. And it's apparently unknown. Oh wait, it's decimal. Ah. $119. Okay, so it's the return from interrupt which fails. Okay, so maybe adjusting the stack pointer here didn't work. Because yeah, we push here, so we should add 12. Not better, but different. Not sure why we get that though. So yeah, this is outside any physical memory, so the emulator is not happy. Do you have a Steam account? Why do you ask? I'm curious. Yeah, I have a Steam account, but I'm curious about why you ask. So how can I debug that? Well, the easy way would be, for example, to add an infinite loop here, run the thing. I could use a breakpoint though. Okay, and then displaying the registers. Okay, I don't really see anything invalid directly in the registers, so it's probably on the stack. Let's take a look at the stack. Okay, info registers. So perhaps he wants to play. That would be the expected reason, right? But what I don't understand is why do you want to play with someone who streams code, right? Maybe I'm not playing, you know? This is snowy. Oh, yeah, I saw someone else do that. That's why I tried it. I didn't know it was really to Steam. So X with a format which is a repeat count. Let's say we want. So what's a return from interrupt like? What does it need? Right. Interrupt return. So PE should be enabled because we are running in protected mode. Okay, so that's it here. NT, I don't remember what it is, but I'm pretty sure I'm not setting it to 1. Operand size is 32, yes. Then pop the instruction pointer, pop the code segment. Okay, 16 bits discarded, okay. So it's a 32-bit pop, yes, okay. Then temp E flags is popped 2, so we have 3 pops. Okay. Yeah, okay, so 3. That's the number I want. Then we want it in hexadecimals and we want to print words. And the stack pointer is this. And I really don't see that weird address that we had before. I don't know where this comes from. So this is a low address, this is a high address. So when popping... Oh wait, this is the stack, right? Yeah. So this is the first thing that gets popped, which would be the instruction pointer, which makes sense. It looks like a reasonable code address, which we could actually check. Then we have the code segment, and then we have the eFlags register. So to me, it looks alright. So what am I doing wrong here? Yeah, again. What am I doing wrong? Let's use another emulated trick. -d int to log all interrupts. .24, so 24 is 36 because this is hexadecimals. And this is decimal. I should actually print them in hexadecimal maybe. Okay. That is weird. I'm going to replace that loop and look at it in more details. This is not helpful, unfortunately. Also, maybe it's not the first interrupt that fails, maybe it's the second, although I didn't see a second interrupt. Instead of 3, let's use, I don't know, let's use 8. To have more data after the stack pointer. I still don't see it. So what may be happening is that we are returning to the code that was interrupted, but maybe we have changed that code somehow. Or a data that the code uses. And then this code runs, well, jumps to something that is illegal. And because we don't have paging, we can't really catch those errors, which is a bit annoying. So the interrupt handler itself looks good, or maybe I changed registers. Oh yes, that's stupid me, stupid me, stupid. Yeah, actually just add 4 here. Then load registers and then skip only the vector and error. Much better. So yeah, we corrupted the entire context by shifting once too much. Okay, that works much better. Also, the code here means that we can only handle interrupts, external interrupts, because the vector is shifted by 32. So that's not... That doesn't allow the handling of exceptions, which are below 32. I'll have to change that. Okay, so what I have now is 2 threads running with cooperating scheduling and interrupts that can occur at any time and are not going to crash the system because the state of interrupt threads is correctly preserved. Let's commit this right away. No, not this. Oh, I changed the test, and I slightly changed thread. Yeah, that's okay. Okay, so that's the first thing that I wanted to do. Hello Mechrono, I'm new to the series and I'm only a noob when it comes to assembly. That's okay. If you want to ask things, you just ask what you want to know. Because yeah, this is... I'm going a little fast maybe, But at the same time, yeah, I've been over this, so I expect, like, by default, I expect that either people are not interested in it or they already know. And I'm really interested in what you're doing. That's nice. So yeah, again, if you want to know, if you want to understand stuff deeply, like in detail, in real detail, because that's what the project is about, just ask. But know that what I'm doing here now is really, I'm talking about it, which is why you see absolutely no comment. Well, not absolutely, but very, very few comments. The result, once I walk over the code again off stream, for people who didn't watch, is actually quite commented with lots of details. So in the end, it will be documented, but so could you please explain what you would need in an OS to make it an OS? That's a tough question. The word operating system is vague, really vague. Anything that allows you to extract what your machine can do is usually an operating system, or a middleware, or a kernel. So we talk about kernels usually when you have something around it, like a shell. That's the original view. You have the kernel, which is central, and you have the shell, which is around it. But you can have a kernel without having a shell. You can call it a kernel. It's not, there isn't a formal definition about that. Now, an operating system, what usually makes an operating system is that you have tasks or threads. So usually you have multi-threading. It's not compulsory. You have very small operating systems which don't have threads and provide other kinds of services. And these services will generally be like memory allocation. That's really probably the most basic stuff to have, but even some systems don't provide dynamic memory allocation. Very small real-time systems don't have dynamic allocation. You need drivers, usually, so maybe not like that. They may not be considered part of the system itself. They can be used, they can be seen as like applications, something that extends the system. But you usually need a few core drivers to handle the processor, at least. Memory, usually, and time, for example, is also quite essential. So that would be really the basic stuff. Basically something that knows and handles your processor, handles your memory, and handles time. These are usually the three core services that you need. And then, for example, you might have virtual memory, and you might have multi-threading, you might have multiprocessor support, you might have an extended or multiple extended driver stacks. So that's what you expect from a system usually. From what I remember when working with the MASM kernel, I don't know. But they're used to turn ASM to machine code. Oh no. No. Are you doing that manually, or do you not have to do that? No, that's not a kernel. That would be an assembler. An assembler turns assembly code into machine code. And yes, I'm using an assembler here. The GNU assembler with AD&T syntax, to be specific. So, now that I'm done with interrupts, I'm going to take care of all the small details that I need to in order to make threads really work. And I'd probably start thread sleeping. So let's see. For now, this is good. So this is basically this is the main scheduling function. And this is the main scheduling algorithm, and the algorithm just picked the next one. That's the current algorithm. So it's very simple, it's pure round robin, and currently it's completely cooperative. So really, it's extremely simple. What I'd like to do now is make threads sleep. And before, I'd like to make sure that I'm not Forgetting something obvious. Yeah, stack size alignment. This function here guarantees that memory that is returned is correctly aligned, so that it can be cast into any built-in type, which basically means that it's aligned to the word size, which is 4 bytes here, because it's a 32-bit processor. We have the idle thread, we have the yield function, we have preemption control, okay. So yeah, reschedule, if necessary, will be implemented later. So yeah, I'm going to implement sleeping. So the function is this one, thread sleep. Not sure why I'm passing the thread. That doesn't really make sense. Doesn't make sense at all. Okay. So in order to sleep, it's actually very simple. You basically change the state of your thread, and then you schedule. And the scheduler is going to move the thread out and move another thread in, so dispatch another thread onto the processor. And because the thread is now asleep, it's not going to be in the run queue anymore. So the run queue only contains threads that are runnable. That's the logic, the basic logic behind it. So I need a state. That's the first thing I need. Let's use an unsigned it. We could use an enum actually. But I like in C I don't really like enums because the way they're defined makes them ints or unsigned ints basically. But I could. Like let's use an enum just for the example, an anonymous enum. Or let's try. Thread state, and then we have thread state sleep, and actually run will be 0. Okay. So thread init. When a thread is initialized, the policy I have is the same as POSIX, which is to make it runnable directly. For example, when you use pthread create in user space, the thread that you get runs immediately. You don't have another function like pthread start to make it run. And I'm going to use the same policy. There is actually a good explanation of that in the POSIX specification, and for the same reasons I'm going to do it the same way. So state is above node, so it's here. Thread state is thread state run. Okay, so threads are initially runnable. Now thread sleep is going to have a few constraints. I'm going to force preemption to be disabled and to actually be strictly 1. Because then preemption is going to be used as the mechanism to create critical sections in which you can sleep. So I need the current thread. Okay, so yeah, when I told you that I already expected this function to be called from other functions, this is what I was thinking about. What's the reason behind it? Could you explain it? if it isn't wrong. Behind what? Hello, Medisic, by the way. Can you precise what you're, because of latency, I don't exactly know what you're referring to. Oh, you're talking about the enums, maybe? I would assume. Oh, that. Okay, so let's take a look. Is there a nodes or rational here? Okay, is there another man page? Let's take a look at the POSIX site directly. So system interfaces, pthread create. Basically, there are two reasons. The first is that it makes the interface simpler. You don't have two functions, you just have one. The second, which is much more important, is that it removes a transient state. Like, not running, but about to run, running for the first time. It's a special state that we really don't want to have. Because with POSIX, the way you handle thread state is through other concepts like condition variables or semaphores. You never suspend the thread directly. That's not exactly true. You can send a signal, which would be sigstop, for example, which does exactly that. But then it's handled only with sigcont. And it's considered bad practice because you can't synchronize the state of the thread with whatever you're currently accessing and changing, for example, in a critical section. And usually you suspend threads because of critical sections. So rational. A suggested alternative would be to define two separate functions, create and start, or natural, etc. Yeah, so Ada, for example, has that. It was rejected by the standard developers for many reasons. The number of calls would increase, so additional burden. The second call, however, could be avoided by the additional complication of a startup state attribute. So yeah, you could have another attribute which says that, a bit like detach, for example, it could be started but not started. So yeah, that would be the state, and this is really the main reason. You need to specify the behavior of the thread operations. So that's it. This state, created but not started, can be emulated by having a condition variable in the user applications. Basically, they decided that it's complicated enough as it is. Let's move the burden of starting the thread, of synchronizing the start of the thread with something else, to the developer instead. So if I want to create a pause thread, I need to pause it from inside the start routine. Yes, that's it. Exactly. And it seems cumbersome. It seems heavy. Like, we could wonder why they would want to put the burden on developers so much. What happens in practice is that you seldom use threads directly. You use threads to implement higher abstractions, like a work queue. And you implement this synchronization feature once, basically, and then you use it through your abstraction of work queue or message queue or whatever you have. So it's I've had that problem many times, and I don't really consider it a problem. Like, it's not something that makes me frown, or that I consider frustrating. The thread API is meant to be low level and to provide control up to some point. And as the developer, I really don't mind having the thread start automatically, especially if it's detached, or controlling its start manually. That's it. So I also speak from experience because I've worked on the herd system, as you may or may not know, and the herd system actually allows that. You have the thread suspend and resume calls, and you have even other calls like abort. And these calls are meant to change the state, the context of a thread. For example, to implement fork. And I can assure you that we have very tricky bugs because of that. So maybe for like a very low level interface like this one, this is a microkernel, so the implementation of threads and clone is in user space in the C library. Maybe that's needed. I don't know. I don't think it is. I'm not there yet. I don't have user space on my system, but having worked on this, I'm almost certain that it's possible to have an interface at the kernel level which is very close to the POSIX interface and still works and allows a lot of control to the user code that implements the user space system and libraries. But I can't prove it yet. When I have an implementation, I'll show you. But I'm not focusing too much on user space currently, so yeah. If it's still possible to do parsed threads, it makes sense to make a more common case simpler. Yes, exactly. And I think it's a better approach, to have simpler, smaller primitives that allow you to build what you need on top of them. This is the approach I used, for example, in X15 in the timer interface, just to show you how it can be done. So this is the timer interface, and basically you can see that I only really have 2 primitives to implement a timer, well 3. I have the initialization of the timer, where I give the function and some flags like if the timer is detached or not. I think it's that. So detach, interrupt, high priority. But really these are specific flags. It's a bit like when you handle a signal, you can, a timer actually. When you handle a timer in user space with POSIX, you can tell whether your timer will be in a signal context or in another thread context. Timer create, I think, or set time, yeah. Set time. You have a timer spec here, I think. No, it's not exactly that. Possibly the flags, I don't remember exactly. But you have a feature that allows you to specify how the handler is run. Maybe create, I don't remember. Sig event. That's it here. So in the sig event structure, you specify how the notification is handled. So either it's in the signal context, which is basically the same as interrupt here. You have an interrupt, you directly handle your timer in interrupt context. Or you have a thread, as if it were the start function of a new thread. And this one is Linux specific. So yeah, and here I have another option which is high priority, but still, still in the context of a thread. And I really have those 3 functions only, schedule and cancel. So you can see that there is no concept, for example, of a periodic timer or a one-shot timer. All timers are one-shot, and you can reschedule from the handler, and that's how you implement periodic timers. You see? A simpler interface which you can use to build higher abstractions on top of it. I think it's really the best approach. So I like the reason they have against this new transient state, and I also like having less states in general. So I completely agree with how it's done in POSIX. Okay. Let's write it like this. So I have my thread. I make sure that the level of preemption is 1, not 2, because then how can I sleep if the preemption level is greater than it should be. The fact that we want the value 1 here means that we disable preemption once before sleeping, which is completely normal because sleeping means changing context. You can't change context if preemption is enabled. If preemption is enabled, you might be interrupted in the middle of context switching. And you cannot make sure that the context is correctly saved if you don't disable preemption. At the same time, if it's not 1 and not 0, so if it's 2 or greater, it means that you may not sleep, because if you re-enable preemption once, like it's supposed to be done, for example here, preemption will still be disabled. It will go from 2 to 1, so it will still be disabled. And it makes no sense to sleep if preemption is disabled. Right? Preemption means that you cannot change the thread that currently runs on the processor, so this would make no sense. Which is why I have this requirement, a very strong requirement on the preemption level here. Also the state, that's obvious. You cannot sleep if you're not running, because you would already be sleeping and waiting for something else. So that's one thing. And then we're going to call thread runQSchedule. So there is a catch here though. Yeah, I should probably disable interrupts too, because this function expects interrupts to be disabled on entry. For the same reason, you don't want a context switch to occur within your interrupt handler. Also, this means that we disable interrupts before disabling preemption. I guess we should disable preemption before disabling interrupts. I don't remember exactly how it's done, because there is a precise order and a justification for this order. Yeah, preemption first, interrupts later, that makes sense. So this order here is wrong. And the reason why it's wrong, well, it's not really wrong, but if you disable interrupts first, and you have why did I have this order? I don't remember exactly. I don't think it's really important, to be honest, especially on a single processor. On multiple processors, it might make sense, because, for example, if you have another processor that, for example, checks your run queue to migrate a thread from between two processors, it might do it while in interrupt context, because preemption is not disabled yet. That might be the reason, I don't remember exactly, but I don't think it's that important. But I want to use the same order everywhere, and so here, if I expect the preemption level to already be disabled, and I disable interrupt later, I want to keep that order everywhere. So okay. Oh yes, there is another obvious reason. You want to disable interrupts as little as possible. That's probably the main reason, and that's why I didn't comment it, it's obvious. You want your interrupts to be disabled the least possible, because you want to handle events as soon as they occur. So here, when you disable preemption, it doesn't disable interrupts, which means that you can still handle events that occur between those two calls or during this one. So while disabling preemption, for example, which minimizes the critical section here. So yes, preemption first, interrupts then. Okay. By the way, On restoration though, we should make sure that the state of the thread has become run again. Because here normally in this function the thread should be sleeping. So it can only return from the function if it has been awakened. So yeah, I probably want to have that here, because if I have an interrupt, like imagine the code is like this. Here interrupts are still enabled. And if I have an interrupt and the handler of the interrupt sees the state of the current thread as being asleep, it's weird, you know, it's a very weird transient state. So in order to avoid such a transient state, I make it impossible. By changing the state only when both preemption and interrupts are disabled, it becomes impossible for another thread, or any other code actually, like an interrupt handler, which is not really a thread, it becomes impossible for it to see this weird transient state where the thread is not asleep. Well, the thread is asleep, but still the current thread. Okay, what else do I need to do? I think that's all. Yeah, I think that's all. So in order to use thread sleep, we need to disable preemption before calling it. Okay, so let's sleep, which means that we need to disable preemption first. And we could actually keep it disabled because we have an infinite loop, so that's fine. Okay, so now both threads are going to sleep and will never be awakened, which means that the thread which should be running is the idle thread. Too few arguments, yeah. Now, I haven't changed that function though. So here, I get the previous thread, I get the next thread, and if the previous thread state is thread, well, I should probably make an accessor. I don't know. Probably not. For now, not. If I don't need it, I don't write it. And what I want to do now is remove it from the run queue. So I have an add function. Right here I'm going to write a remove function. Okay. So how do I use my linked list again? Just remove. Okay, there is only the node. This void here basically silences a warning about this argument, a warning that the compiler would emit saying that it's not used. This basically means nothing, but makes the argument used. Shouldn't be run queue and not thread run queue. Yes, you're right. Where? Why? Oh, you mean here? Yes, it's passed as an argument. You're right. Which is actually very good. We want to minimize the use of global variables directly. Okay, so I should still have my interrupts. Okay. And normally, if I use the debugger to watch the state of the machine more closely, we should see that we are in the idle thread, just idling. Another way to see it would be, for example, to use stop and check the virtual machine process, which is this one, and see that it consumes almost no CPU. The CPU usage you see here, so it's the yellow line, right? It's this one. Sometimes it consumes a bit of CPU, and the reason it does is because the emulator has its own timing needs, like to emulate a timer, usually. But that's basically it. So, okay, we have both our threads sleeping, that's good. Now what we want to do is waking them up. So how could we do that? Oh, also, a strong requirement is that waking up a thread should be doable from interrupt context. Because usually, you don't do much in an interrupt handler. You basically read or write some data, so you make a very low-level transfer, and then you wake up a task to handle whatever transfer you did, or for example, to queue the next transfer. For example, when reading from a disk, the disk would raise an interrupt, or the DMA controller would raise an interrupt, telling the main processor that the read is complete. So what you would do is that you would read from the device, and sometimes you don't even have to read from the device because it's actually controlled with another way, so you would only wake up a task or a thread. Let's talk about threads here. I'm a bit too used to Linux and other systems which call them tasks. But basically you would wake up a thread, and that thread would then access the disk, read some ring buffer, for example, and then clear a flag stating that that part of the ring buffer is now usable by the disk, or the network card, or anything. So it's really important that thread wake up be usable from interrupt context. One thing I want to handle immediately is that the target thread could be self. In which case, obviously, waking up yourself makes no sense, because if you can wake yourself up, you're already awakened. One thing I did in my other kernel, if I remember correctly, is also handle a null pointer. If someone, well, some code wakes up a null thread, it's like reasonable to assume that they haven't reached a state, or they are in some state where there is nothing to wake up, and so it saves some conditions throughout the code. But unless I really need it, I'm not doing it again. Like we could actually assert that the thread is not null here, because we don't have paging, and address 0 and next to 0 is actually mapped, which means that we could have accesses to null pointers and not even notice it. We wouldn't have something like an exception or a page fault, which is an exception. So let's use assert here. If you work on very old ARM processors from the 90s, beginning of the 2000s, you may have processors configured with, for example, the exception, well, it's the exception table at address 0. And if you access that, if you read it, you'll have garbage. If you write it, you may just completely screw your entire system by preventing it from handling interrupts anymore. So you'll probably have a fault. So it makes sense to check for null pointers on these, like on some architectures, especially if you don't have virtual memory. Okay, so we have a thread. Let's make sure that the state of the thread is asleep, but before we do that, again, we must make sure that we are in a state that prevents anything else on the machine to change. We use both preemption and interrupts to implement critical sections, so let's do that. Again, wake up can be used from any context. Thread context, interrupt context, with preemption disabled, preemption enabled, interrupts disabled, interrupts enabled, it doesn't matter. It must handle all cases. So let's save the flags. And I said that we disable preemption first. So disable, which we will then enable. And then we disable interrupts. Okay. So now we can check the state of the target thread. We know that because we have a single processor and we disable preemption and interrupts on this processor, this critical section cannot be interrupted by anything. Nothing else can run. So because of that, we know that the state here remains stable for the duration of the critical section. And that's how you should think about critical sections. Critical sections make your data stable. You know that your data cannot change while you have whatever protects your critical section. Oh, actually we don't want to assert, because maybe we're waking up a thread which has already been awakened for some other reason, like a spurious wake up or anything, so we shouldn't do that. Instead, we should just check the state of the thread. So thread state sleep. If it's already running, there is nothing to do. And if the thread is asleep, we wake it up, sorry. And we should probably use a method for that. Actually, we could push that elsewhere. Run queue schedule. Run queue schedule deals with the state. Okay. So run queue add. Run queue add could make the thread awaken automatically. We could do that, and remove could make it asleep automatically, right? Yeah, because here we don't change the state. We remove it if the state is already asleep. So maybe we don't want the queue remove and run queue add functions to change the state. Okay. What we could do though is have assertions on the state of the thread on entry. So for example, when we add a thread, we must make sure that the thread is runnable. Or running, really. Okay. And obviously when removing, we must make sure that the thread is, well, different from running. We could have, like, I expect another state which is going to be like dead when we implement thread destruction. It's very close to sleeping, but it's not sleeping. It's sleeping and being unable to wake up and just waiting for destruction. And I don't expect any other running state. I expect 2 sleeping states, but only 1 running state. So I could have accessors here. I'm using the members too much already, so let's have accessors. Set state. Or should I have functions like set thread set state running directly instead of passing the argument? I don't expect the states here to change too much. That's okay. No, I don't really like it. Like sleeping, maybe. See, that would be better. Set running. Let's use is to make it more a little more significant. Okay. Yeah, that looks good. So let's walk over all the states and fix that. Okay. That's the only reference we have left. Let's write the accessors. Well, before we write the accessors, I want to finish the function I was working on, assuming the accessors are already implemented. So if thread is sleeping, we set it running, and then we add it, and adding it makes sure that it's running. Okay. And so when we add it, currently there is nothing to do. But later we'll probably have a flag. For example, when we when we implement priority. But I'd really like Metal Snake to do that again. That's a little sad that he's not here, he's not around. Okay, but normally that's it. One problem I have currently is that there is nothing to yield implicitly. The yield must be explicit. You have what we have now is called cooperative scheduling, and what I'd like to do is implicit yielding before we have timing, before we have a timer, and it should be done here. We schedule if necessary. So for now I won't have it, but that's probably what I'm going to add right after. Oh yes, I forgot that. So thread is okay. Let's write our accessors right here. Running first. Damn it. Well, I can just reuse that as a template. And I should change the name of the state immediately. Okay. What else do I have? Thread set running or sleeping. Okay, so set sleeping. And I have set running too, actually. Okay. Thread undeclared. 165. Oh, because I put the prev actually. Okay. Now we need a good test case. Do you still sometimes visit Orgrimmar? Not directly, but I keep watching all the Warcraft streams. And it's a game I really liked, but it's a dangerous game. You know, it's so time-consuming and it can get so toxic. But like most current popular games, I assume PvP games mostly. Okay, so let's take a look at how we can test this. We probably need two functions now. League of Legends. Well, it's World of Warcraft, but League of Legends developers are actually ex-Blizzard employees, I think, Riot Games, who worked on Warcraft 3, for example, and StarCraft. I think the original version of League of Legends used the Warcraft 3 engine, if I'm correct. I don't remember exactly. Okay, so let's say that we have how could we implement that? Let's make the threads wake up each other. Can we do that? I'm gonna write a test1 and test2 function. Let's see what we can do with that. Can we actually make them wake up each other? Left over coding, I think. Well, I did code a lot before and during and after, so no, not really. I left because I got old. I wasn't as good in arenas or PvE as I used to, and I really liked, being good, and really didn't like being bad. And yeah, I had other things to do because it's very time-consuming. So the whole together meant that yeah, I had better things to do. But this sucks a little. The problem I have is that I'd like to pass them as arguments here, but I can't really do that because they're created sequentially. Which means that when I create that thread, I don't have the other yet. Right? So I'm going to use global variables, exceptionally. Okay. And so it's not going to be the same function. Alright. Now this also means that for a time, so when this thread starts, this variable here is going to be null. And actually they're pointers, yes they are pointers, so I must keep in mind that these pointers, and this one at least, but let's not make the code fragile, and let's just assume that both can be null, and I'll be fine. Isn't passing null as a parameter a smelly smell? Why would it be? Like, the argument here is not used, so why would it be? To be honest, most of the time when you create a thread, the argument is null because it's many times threads get their data through other means, like a message queue, for example. But I don't have yet. I don't have a queue yet in my system, and I probably won't have a queue. Well, I have a list, and I could use the list to pass messages, or arguments, whatever you want to call them, and use preemption, for example, to protect the list. I could do that, right? What I'd really like to have is mutexes and condition variables, but I can't have them yet, because I need to be sure that sleep and wake up work first. Okay, so let's write this function first. We disable preemption, okay, then what do? We want to wake up thread 2, that's basically what we want. Okay, so if thread 2 is not null, we want to wake it up. So what we could do though, actually I really like them to wake up each other, to sleep and wake up each other. So one is going to sleep first and be awakened by the other, and then they're both going to do the same thing. Maybe I can factor the code, but since it's just test code that's not meant to remain long, I'll do it the quick way. Also, I'm not going to sleep if I was not able to wake up thread 2, right? Because then if I don't wake up thread 2, I'll never be awakened again, right? So thread wake up, thread 2, and then we sleep. Okay. It would be nice to have a condition though. Is there a difference between for and while true? That's a frequently asked question. There is a difference, but not in the generated code. The generated code should be exactly the same, provided you have basic optimizations enabled. But semantically there is a very small difference. While true makes no sense to me. While true means, like, how can something true, which is always true, have anything to do with time, which is implied by while? Whereas for just means, you know, for each, for continue, you know, it's simpler for me to think about. But who cares really, you know, it's extremely minor as a difference. I just got used to for, and that's it. It's simple for me to think about. I use it all the time, and that's it. So let's have a condition, okay? So let's use a boolean, for example. Thread 1 awaken, and then thread 2 awaken, okay? So when thread 1 enters here, he's going to... He doesn't care really about the fact that thread 1 is awakened or not, but let's make it clear in case we want to debug. Thread 1 is awaken, okay? Which means I want to include std bool. While true is true, which, well, is always true, makes sense for me. But that's a problem. If you use while, you basically assume that something may change over time. Because otherwise, why would you use while? You know? For me, it's counterintuitive. Okay, so here we declare that we are awaken, and so if thread 2 is valid, we wake it up. Okay, so we set it, thread 2 awaken to true. We set basically the condition, the predicate, also it's called. We wake it up and then we sleep, but we should never sleep like this. We should always sleep in the loop, and this time I'm going to use while. While thread 1 not awaken, we sleep. Okay, and so thread 2 is going to set this predicate to true, which means that because I'm about to sleep, I'm going to... Yeah, I could do this actually. Thread 1 awaken is false, and I'm going to use do while. Because there is no point checking whether thread 1 awaken is true or false on the first iteration, it will always be false. Okay. Okay, and so I use preemption here, which means that preemption is always going to be disabled, except when calling thread sleep. Because obviously thread sleep means that the thread is going to sleep, so another thread is going to take over the processor and run, which implies that preemption is disabled. By the way, hello Satire. Okay, now thread 2 is going to be very close. I don't need that, by the way, do I? I don't think I do. I only need thread 2, right, yeah. Okay, so same here, we disable preemption. The difference is in the order. So thread 1, let's assume that thread 1 might be null, like the other, okay? But what we do first is that we sleep.
Walking a fine line between pagan and Christian.
Okay. So because we're about to sleep, we set thread 2 awaken to false. Okay. Okay. Then we set thread 1 awaken to true, we wake it up, and that's it. So it's basically the same, but in the reverse order, so that we have one thread that actually starts and the other that continues. Unused variable thread, line 92. Ah, that's right. Okay. So I probably won't see anything, because those threads actually don't print anything, which is stupid. Let's make them print something when they wake up. And actually, let's have so waking 2. Let's write like this, so that we don't have as many new lines. It will reduce scrolling. Yeah, that works. So the threads are indeed sleeping and waking up each other, and it seems correct, it seems to work. Technically no, but later on it might be a good choice where you to introduce a condition for loop. For looks like it's extracted from 79's alien. I still prefer 4 because yeah, I agree with you that it's not pretty, so it's actually quite ugly compared to everything else in the code, but again, I think the semantic is more important. And the semantic is just that 4 without anything just means, you know, it's an infinite loop. Whereas while true, again, I have a problem with while true, because how true could possibly not be true? So why do you want to check it again? But who cares? Again, we're talking so much about something that is so insignificant. As is often the case, and that's, by the way, that's what bike shed discussions are about. If you don't know about them. The low triviality, basically that trivial issues get a lot of attention and difficult ones don't. So there is an inverse proportionality between the two. How could while true be possibly not true? Well, actually, what I said is how true could possibly be not true, you know? And this really is, that's the logical problem I have when I see while true, you know? When I read that, my brain is frustrated because it can't understand how true could possibly not be true, really. That's why I like 4 better. Okay, so I have those 2 functions. Let's take a look at the diff. That's the test code. Okay, here we have states, accessors to states, additional assertions, and we have sleep and wake up, which are very, very small. And this is the reason why they're so small is because this is a single processor system where it's very, very easy to guarantee or to create critical sections. Here is how it looks like on a multiprocessor system, which also handles timeouts. That would be the same function. So you can see that it's a lot more complicated because it has to handle the timed cases. It uses a spin lock, which is a lock between processors in addition to that. So the waiting channel is not really important here. We have the state, so here I use a direct access to the member. RunQ schedule actually has the same name, we have the same assertion here, and then lock again. We have to check whether the timer was, or the sleep was cancelled or not. And then we have an interlock here. We don't have an interlock here because we use preemption. The interlock is used when synchronizing between multiple processors. And so yeah, we have those tricks here, which are not obvious to understand. We have the same requirement here, and then we have an error to indicate whether the sleep was correctly awakened or if it timed out. And so obviously you have the timeout function here, which wakes up with an error. So that's the code here, all this. And then yeah, wake up command, what does it look like? That too is quite complicated again because it's multiprocessor, so you have the check of the state that is already difficult. You have to lock the run queue, which is difficult because while locking the thread might be migrating, and then you have thread that may not be migrated if they're pinned or not. And then we need to select the run queue. I don't remember what this one is. Okay, select run queue is here. So on which processor you want to dispatch a thread, and then you have the run queue wake up function, which I don't have, by the way. I have add. I have this one, and yeah, wake up is probably the next thing I'm going to implement because I want to handle this flag. But I don't know if I can do that really, like, right now. Can you maybe explain the difference between locks and mutexes? Lock is a general word, mutex is a more specific word for the same thing, basically. Mutex means mutual exclusion, so you may only have one thread accessing your critical section, whereas a lock, like you might have read-write locks, shared exclusive locks is another term for them, and then the implementation of the lock or the mutex is also different. Usually what we call mutex implies sleeping, so relinquishing ownership of the processor. It's not really ownership, but yielding the processor to some other thread. You might also have spinning mutexes, so spin locks, and I use the word spin locks and mutexes differently because the way, well, not really the way they're implemented, but more like what's allowed in the critical section is very different. Usually spin locks disable preemption, which means that you may not sleep in a critical section protected by a spin lock. The reason being that if you sleep inside such critical sections, another processor using a spin lock may just be spinning, waiting for the other processor to exit its critical section. But because you're sleeping inside the critical section, it might take a long time. So by sleeping, you basically make all processors potentially very late, and so the system is extremely slow at some points. So spin locks usually disable preemption and restrict what you can do in the critical section, whereas mutexes allow you to sleep. So you can use them for more expensive critical sections that might take a longer time to finish. But again, lock is a very general, broad word, whereas mutex is slightly more precise because it implies mutual exclusion. So really one thread inside and all the others waiting. And the way they wait is either active, so spinning, or passive, which is sleeping. Okay. So what do we do next? We could do mutexes, but again, I'd like to see with Metal Snake if you can do that. We have, so what do we need? Join, oh yes, thread destruction. That's something I'll do next time. Not now, certainly not now. Shit, when I said it was simple, I didn't think it would be that simple, to be honest. Like, these functions are fucking trivial. Really trivial. Like, it's so small. Okay, so let's do something instead. Let's have runQ wake up here, which is going to use runQ add, but also set this yield flag. And let's assume that every time we wake up a thread, that thread runs immediately. We don't have priorities yet. That's something I'd like to implement, but again, I want to see with the Metal Snake what we do about that. So before we have priorities, let's consider that all threads have the same priority, and so let's implement a default policy that every time you wake up a thread, that thread is going to run. We could do that. But it won't change the, well, it will change the test code, but only marginally, because like if you wake up here, the other thread will wake up, but the problem is that if this one doesn't sleep, it could yield the processor though. It could yield the processor instead of sleeping. That's something we could do. Here, the reason why it works without a timer, for example, or without explicit preemption points, is because both threads are going to sleep. So when they sleep, there is scheduling. What I'd like to do is make sure that scheduling occurs even when threads do not sleep. But that's a problem because this will require a timer. So that's something we could do next time too. Well, some other time. Basically, what we need to do is thread destruction, mutex and condition variables, priorities. I'd like a fixed priority based scheduling algorithm, which is extremely simple, very, very simple. Timers, and basically the system is done. So it's almost the end. So what we could do though now is make sure that the rest of the system is thread safe. That's something we didn't do. So for example, printf here. Printf disables interrupts. And because the main source of implicit scheduling is timers, so timer interrupts, by disabling interrupts, you mostly prevent preemption. But maybe not. Maybe, for example, this function here may preempt, may call thread yield here. For some reason, we don't know which one. Maybe it uses it uses preemption internally because we expect it to be called from thread context, and by re-enabling preemption, a thread calling this this function here might preempt to another thread. Well, not really preempt, but might yield the processor to another thread because of that. And we want to avoid that. We want to make sure that the thread calling printf, or the interrupt handler calling printf, because again, this is a function that may be called from any context. So when you have code that must be runnable from any context, you want to disable both interrupts and preemption. So that's something I need to do here. And we said preemption first, interrupts next. Hello, Mr. Noru. Print enable. Okay, so that's the first thing. What else do we need to protect? Let's see. Oh, that's all the files. The memory allocator. Yeah, the memory allocator must be protected too. I wanted to use a mutex for the memory allocator though, instead of preemption, but I guess that for now preemption can do the job. Because currently the allocator is absolutely not thread safe. And could we prove that? Could we make the system crash? That could be fun. How could we do that? The problem again is that I don't have implicit preemption. Involuntary context switch is also a name for that. So I'm only going to preempt at well-known points, and those points will not be using the memory allocator. So no, I can't really cause trouble yet. So I guess next time we'll want to implement the timer driver, I guess, so that we do have regular interrupts, and we can count on the system to schedule even if there is no activity, like no activity that would trigger scheduling otherwise. Okay, so let's make the allocated thread safer now. This isn't a bad thing to do. So we disable preemption. We don't want the allocator to be usable from interrupt handlers, so we don't need to disable interrupts. Now this is going to be a problem, okay? Okay, so obviously here, if I have an error and I return with preemption disabled, which is a problem. So I have multiple ways of dealing with the problem, but here the simplest way is probably just to add this call inside this block. But if you have a couple of resources that you allocate or whatever in the same function, and you have an error on one of them, what I usually do is what I'm going to show you, which involves the keyword goto. So if you have, a sensitive heart, you might want to go watch something else. Oh wait, it's actually this one. Nope, it's yeah, it should be this one. So yeah, that would be an example of how to deal with such errors, where you allocate several objects, for example. Actually, it's this. You have two allocations, and you want to make sure that you correctly release your resources. So there are really two reasons why I do it this way. There are other ways to do it. You could have, for example, if, else and go back to the end of your function. You could do that too, and at some points have your free or destroy calls. I do it this way for two reasons. The first is that it makes the release code, so the error handling code, compact, where calls are close to each other. So it's easy to see what resources you have, and destruction is actually symmetric to creation, usually, unless you have weird loops, for example. So in a simple function like this, you have your resources that are symmetrically destroyed or released compared to their allocation or creation. The second reason is that it makes the code fit on the first indentation level. And the policy in my coding style is that the first indentation level is the main case, the most likely case, the case I expect. And corner cases are handled by conditions here. So for example, this would be a corner case. Like, it's very unlikely that allocation might fail. Usually allocations succeed, unless your system is very heavily loaded. So this is a corner case. Same here, you don't expect your object creation to fail. And when you check a variable, for example, actually I have var, yeah, okay. I should actually have obj here. Yeah, sub-obj, that's okay, I don't really care. But usually errors, which are better named exceptions, are called this way because, well, they're exceptional. Exceptional means that they're not likely, they're unlikely. So the most likely case is kept on the first indentation level. It makes it easy for the reader to expect what the code is going to do. It allocates, it creates, it checks, it initializes, and it returns. It's easy to see that. And another reason is that compilers, especially GCC, have heuristics, built-in heuristics about certain constructions. So basically, return, goto, and other keywords like that are considered less likely to happen. So when the compiler sees a conditional jump and the return or goto keyword in the block that depends on the condition, it's going to assume that this block is less likely. And so in the generated code, when you have your jump, the jump will be used for this block, and so this block will move elsewhere. So basically what you'll have in the generated code is that you'll have the most likely code, and then you'll have your first if, and your second if, and your third if, etc. And so in your most likely code, where you have your conditions, what you do is that you check your condition, and if it's false, you jump, and if it's not, you continue. So it makes branching prediction easier. It makes reusing the instruction cache better. So you have all these micro-optimization things that apply to this case here, which you probably wouldn't have in other cases, or you may have, but with less reliable results, because it's only heuristics here. The compiler may not do what I'm telling you right now because it might have other heuristics that are bigger, for example, than the first, and so the end result might just not be the same. But usually, again, it's heuristics. It's statistics basically. It's a statistical approach. Most of the time, that's what you get. And if you look at the Linux code, you're going to see the goto keyword used a lot. Let's try that. Yeah, so the grep is going to take some time, and this is only the documentation, but I guess there are code snippets in the documentation. And I have a very slow disk, not SSD as usual. So it takes time to fill the cache with it. The cache being this thing here. I think the kernel is it's around 2 gigabytes, or maybe 1.5, I don't remember. just the Git repository. 2.5, okay. But 2.5 including all the history. I'm only interested in the last commit. Okay. $150,000 occurrences of the keyword goto. So let's go into the real code. You can see lots and lots and lots and lots of gotos. And the reason is really because of that. I mean, I didn't invent the thing. Do you sometimes play around with higher level languages? Do they interest you at all? Yeah. I use Python. Not much. And interested, yes, a bit. Not that much. But I really like using Python. And I like some ideas in higher level languages, of course. But I don't have the occasion to use them a lot. Okay, so here, like I said, the simplest thing to do is probably this, but you can see that it's very easy to forget that sort of thing. It's basically the same thing as allocating memory. You have an error, you have to free the memory you've allocated. So for example, at work I have another policy, which is that every time you acquire a resource, you branch, and so you branch if successful, and you make sure that this is called. Like this would be completely forbidden here unless you have success. So it's completely different in the way you think about it. Here I test the error first, and with that other policy you would have to test success first, for example. It's a very different way to think about things, and the resulting code is very different. I have a very linear code close to the first indentation level, and here we'd have a code that is like a V or an arrow, whatever you want to look at it. So if, and then you close your blocks. Okay, so the malloc is done. So why only here? This critical section goes from so this line to this line here. This critical section protects global data, so data that may be accessed by other threads which call memalloc or memfree. Here I'm testing a local variable, here too. Here I'm testing a global variable. Well, I'm using a global variable, which is the only free list I have. So this requires protection. And here the payload here is just access to the block that we've just allocated, so it's local. Testing the pointer is also local, so this is where I end the critical section. Same thing here. And voila. So printf is good. Panic should depend on printf, I guess. Yes, it disables. We should disable preemption though. So we disable preemption, we disable interrupts, and then we printf twice, 3 times, and then we halt the processor. What are you thinking about exactly, Helosia, when you talk about higher level languages? Do you have an example in mind? And something that you think might interest me? That you think is interesting, for example? The pick. That's an interesting case, I suppose. So let's take a look at the interface and then the users. RQ enable. I would assume the only other would be the UART driver for now. Okay, so the interrupt handler is here, and then we have setup. The setup functions are all run before scheduling is enabled, so we don't need to do anything with preemption. And the interrupt handler is obviously run with interrupts disabled, and preemption cannot occur in an interrupt handler. It's disabled. So we don't have anything to do. We already checked that interrupts are disabled. What we should really check is that we are in interrupt context, which is slightly different. Because we could be in thread context and disable interrupts, which doesn't prevent preemption from occurring. But it would only be explicit preemption, like yielding the processor voluntarily. So you need code to do that, and because that code here doesn't do it, there's a guarantee that it cannot happen. So I don't think anything needs to be done here. Boot is only at boot, so no scheduling. CPU not yet, but this might happen. Format doesn't care. Just check that. Main doesn't do anything except the tests. This has been done. This doesn't need to. Well, it has been done too actually. This too. This doesn't care. This is done, and this. Yeah, let's check the UART driver. So for now we have a very small driver. Again, it's just an interrupt handler, which holds printf, and printf may be called from any context, so that's good. Setup is called way before scheduling is enabled. This thing though, that's interesting. So this function is called from, oh, for now it's only called from the interrupt handler, right? No, it's called from printf. Yes, it's called from here. And so it's called with preemption and interrupt disabled. So we might just check that the state matches what we expect. Okay. 91 in UART. One very nice thing with low-level systems like this is that you have no environment, you have no libraries, which means that there is. Well, it may happen with a bigger code base, but with such a small code base, the chances that you include headers indirectly, like that you include assert .h by including another header, are a lot smaller than on a hosted environment where you have a C library, for example, and it makes you learn all those headers, like stddef, for example. Do you know what stddef provides? Or stdint? Well, stdint is more well known. But stddef is something that I almost never see in other code bases. Okay, I thought I committed it. That's bad. Let's see. I want to commit that. Thread C, thread H. Have you seen the little book about OS? Seems like an interesting learning project, 32-bit though, and very much Unix flavored approach. No, I haven't. If you have a link, I'm interested. little book about OS development. Maybe I've seen it actually. I think I've seen it. I think Metal Snake talked about it. Yeah, and it's extremely x86 32 bits oriented, and I'll be honest, I don't like it. Why exactly? I don't remember. But basically, I think it refers to too many things that are obsolete, and people shouldn't care about them. Segmentation, for example. Well, okay, maybe it's not that because the chapter I read was bigger than this, so maybe I'm confusing. I'm mistaking it with another system, another book. Sorry. Yeah, it's not about the theory. That's a good one. Yeah. No, it's not the book, I remember. Okay, that's something completely different. Good. So it looks quite good, and it talks about file systems. There is no file system in the system I'm currently writing. I'm making something very small. This one, yeah, it's probably Unix flavored, as you say. But mine is more oriented to introduce people to very small systems. The kind of systems that you may find in very small IoT embedded devices, for example. Although IoT currently uses a lot more than those older systems. Like, you need at least networking today. You can't do much without networking. So you have a very small system, like the one I'm writing, and then you have stacks that you can easily integrate into the system. So a USB stack, a networking stack, and yeah, usually a file system stack too. So a stack because you have a driver for the MMC or SD card, or the flash, whatever, and then you have a file system on top of it, and then usually you have a C-like interface with file pointers and the common fopen, fread, fwrite interface. But yeah, this one doesn't look too bad actually. Cache babe. Linking the kernel, tin grub. So yeah, I even removed grub from my project because QEMU is entirely able to load the kernel by itself. And so if you want to run it on a real machine, then yes, you need to write a grub entry. Setting up a stack, calling secret from assembly, packing structs. Let's take a look at this, for example. Yeah, okay, yeah, that's good. The frame buffer, so I don't use that, I use the serial ports only. Yeah. Oh, that's right. I don't think I do that at all. That's right. Currently, the driver just writes data and doesn't know whether it can actually write data or not, which means that on real hardware, we'd probably lose data. We'd have bytes that would be dropped because of that. It's true. Segmentation just seems to talk about what's strictly needed. They still explain that, though. Linear address is important, unfortunately. You have three kinds of addresses. You have physical addresses, linear addresses, and virtual addresses. And what all systems currently do is that they use flat segmentation, where all segments start from 0 and extend up to the end of the memory. Well, all segments that are used for code and data, except, for example, thread local storage or per CPU areas, but these are really exceptions. So you have a flat memory model. You go from 0 up to the end of memory, so 4 gigabytes, for example. And so your linear addresses and your physical addresses are the same. So I don't yet explain that, but basically this is what I'm going to explain in the CPU module. I should talk about the IDT too, yeah. The interrupt controller, yes, reading input from the keyboard. So we read input from the serial port, but it's basically the same. Well, not really, because the keyboard is much more complicated. Like, when coding a driver for the keyboard, you have to, for example, handle key combinations, handle key presses and key releases. You have to translate from scan codes into character bytes. And it's much more involved than the serial console, which is why we only made a serial console. The road to user mode, we don't have that. We don't have user mode. We have no virtual memory. Paging, yeah. That gets complicated. Identity paging, yeah, that's good. The fact that they talk about that is actually really great. When I started it a long time ago, I didn't have any reference to what we call the identity mapping, really, which is a special region of virtual memory where virtual addresses are the same as physical addresses. And when you think about it, it's quite obvious that you need one. Because when you enable paging, you have a state before paging is enabled, and then you have a state where paging is enabled. But the only thing you did was just enable paging. You're still running at some addresses. Like the processor just increments the instruction pointer or the program counter, whatever you want to call it, and doesn't really care about, like, it's not going to make you jump somewhere magically when you enable paging. So you at one moment, on one instruction you have a physical address, and on the other, the very next one, you have a virtual address. So if you don't have an identity mapping, it can't work. But usually the identity mapping is very small, and the kernel itself is relocated at much higher addresses. Like this one, yeah, 3 GB. Okay, so yeah, they explain how to offset from virtual addresses to physical addresses. And then, yeah, page relocations, okay. It looks good. Yeah, okay. So yeah, cooperative scheduling with yielding, that's what we've been doing until now. Preemptive scheduling with interrupts, that's what I'd like to be doing, so that's why next time we're going to work on the driver for the timer, the PIT, the PIT, programmable interval timer, separate count stacks for processes, that's what we have. They don't mention separate stacks for interrupt handlers though, I think. Okay, difficulties. Okay. So you may be preempted at any time, including in the kernel. Interrupting a processing kernel mode is a little bit different than interrupting a processing user mode. Yeah, a little bit different, really. Yeah, you have a privilege level change that occurs. It's mentioned here. If you saw the diagram. Handling. Okay. Yeah, it's slightly different. You have basically the stack pointer, well, the stack segment and the stack pointer that are added to the interrupt frame. That's really the only exception, or only difference.
Walking the fine line between pagan and Christian.
Yeah, that's right. And you can see that they don't really go into the details here. I think the book is good. I'll probably link it later. So that would be the first commit, and now we have thread safety. Okay, I'm pushing it for those curious enough to run it. Oh wait. Okay. Okay, that's the commit I didn't have. Okay, so the code is online. You can play with it as you want. So what does it do? Let's take a look, because right now it spams on the screen, but let's assume that it doesn't. So we know that the threads are running. That just won't print anything. Okay. We should still have interrupt handling while the threads are running. What we could do is have a counter, for example, that's a technique I often use to prevent spamming. So let's get back those printfs. Let's re-add the hello world here, and let's use. So what kind of counter could we use? Unsigned long, for example. I. So let's say that I is 0. That would be test 1, although what I could do is just print the name of the thread. So thread name, thread self, I think that's it. And so I'd only print that if I modulo a very big value, say 1 million for example, is 0. Okay. And because I call thread sleep, and because thread sleep, let's take a look at that by the way. Thread sleep calls CPU interrupt save, which should act as a memory barrier through CPU interrupt disable. Yeah, okay, so it's not mentioned, but because this is assembly code that the compiler doesn't know about, it's considered as a barrier. And just in case we have preemption, so here we don't see it because, yeah, it would be here. Okay. So run queue schedule here has the same idea, but actually there is a problem here. The point here is to make sure that when you sleep, everything that had to be done before sleeping has been done, and everything that must be done after waking up has not yet been started. So this basically acts as a barrier. But for example, it may only act as a barrier if you actually sleep, which is the case here, because considering this is the main barrier, which is not really the case, because you also have those interrupt functions that act as barriers. If the previous and the next threads are the same, it basically means that you don't sleep, in which case execution just goes over the sleep, and so the compiler may be able to reorder things for performance reasons safely. So yeah, we only want scheduling to be a barrier if there actually is a context switch, so that's okay. And so, because we have a barrier here, we don't need I to be volatile. We know that this is going to occur. So here, for example, we can write I++ like this. Okay. I don't set IE to 0 here. And 1 million might be, well, okay, it's not too much. It's actually quite good. It's strange that I didn't have a warning, by the way. Very strange. I was used not initialized here and I didn't have a warning. I'm not using W extra. That may be why. Let me check. No warnings. I saved the file though. Where's the no warning? It is used uninitialized. And GCC doesn't see it. What if we disable optimizations? Oh, maybe enable them then. Shit. This means I pushed the commit that that changes the make file. I have to fix that. So, stashing first. Let's take a look. No? Oh, there it is. Yeah, that's probably it. Ah, shit. Okay, I'm going to be lazy and just re-add that in a new commit instead of changing the history to fix it. Okay, so I have optimizations now. Yeah, that's better. Yeah, I know, but yeah, I could, but I'm lazy. Okay. So now we should have those two threads reporting progress once in a while. Actually quite fast. And so we could still handle interrupts in between and we still have the threads running. Okay, great. And yes, they print that at the same time because they're synchronized. They're phased because they wake up each other. So they have the exact same number of iterations. This will not be the case once we have timers. Ugly commit. Don't do that. Obviously. Don't do what I do. But this kind of logs should really be meant for, like, yeah, minor changes. Because here you're basically telling people who read that, don't bother looking. That's the only information they have. Okay, so I pushed it. It works. It's 11:20. Let me just stop now. It's the end of the week. After all. So if you have questions, want to talk about technical stuff, as usual, talk about your experience, things you want to show us, like the little book, for example. That's an interesting thing to know about. Please do. Like, don't wait for the end of the stream to do that, obviously, but it's you have my attention and my complete attention at this time. I can see quite a couple of new names. Hello guys. I can see Zonde. You didn't say hello, Zonde. Too much pressure. I know. But you know, you have to step out of your comfort zone. Hello, Joefish. If you want to introduce yourselves, talk about, you know, your schools, your job, and if you what you'd like to find, to discover, or if you discovered something that you consider helped you, for example. Nice to see some OS development here. Well, this one is a very simple system. I'm going to keep the sleep and wake up code here to show how simple this is, and the main code. Actually, I could divide this to have the data structures in the main code here and show the result. Yeah, okay. Something like this. Were you always programming close to the hardware? Have you ever had the pleasure of developing stuff in higher level language that Java, C# or the like? Actually, so I'm mostly self-taught. I went to school. I didn't learn much. I learned about other things like electronics and math, but not much about computer science or computer engineering. And I started way before school with websites. So I had the pleasure of learning plain old HTML 1.0, the very early versions of JavaScript when we used Netscape. I think it was called Netscape Communicator at the time, I don't remember. I had the pleasure of having lots of web browser specific issues between the first versions of Internet Explorer and Netscape. So yeah, JavaScript, DHTML as it was called at the time. A bit of CSS when it came up. And I went to Perl. I used Perl for CGI, for example. I wrote some CGIs in C and Perl, and so not C at the time, only Perl, because it has a very nice API, and I didn't understand how it actually communicates with the web server. This was magic to me. So I just used the API, you know, like a blind person, and it worked. I was happy. That was for the server side. Oh yes, there were server-side includes also. That's a very old thing that probably nobody uses anymore. On the client side, I then started writing Java applets. And I spent, I think, 2 to 3 years on Java. Versions 1.3 to 1.2 to 1.4, I think. So that's the end of the 90s, if I remember correctly. And then I used Java at the server side as well, so with Tomcat. Does that exist, by the way? Yeah. Apache Tomcat, that's it. This thing here. Is there a Wikipedia page? Is there a history of versions? Oh my god. That's it. That's what I used. 2002. Or no, that's what I used actually. Initial release 332. Yeah. That's very old. So 99, 2000. Yeah, that's about it. I remember Kosher Resin too. Is that still a thing? "12 months ago, yeah, that is a thing." And GPL v3 proprietary, yeah, okay, the classic open source business model. And I remember I switched to Resin because Tomcat was extremely slow. Well, I had problems with Tomcat. I'm coding embedded OS for medical equipment as a job and coding an OS for x86 in my free time, mostly doing assembly if I may choose myself. Really? That's interesting. If you have a link on GitHub, for example, please share. Okay, And that also where I got my start running GSP on Tomcat for stroke database project at a local hospital. Hey. Yeah, I was doing that for myself. Does any of you remember mycgiserver.com? Actually, does Google remember that? Oh, that's still a thing. It's been connected. Really? Oh, that doesn't look like a real site. It looks like a domain that is not registered. Well, failed to load page content. Wow. Ah. 2004. Yeah, so I remember this hosting website because before I hosted Java applications myself, I used that hosting site, and I remember that I was using them to host some stuff, and so at the same time I was setting up my own server, and while doing so I identified security holes, like potential security holes, like accessing files outside your own directory, for example, modifying files that you shouldn't modify, for example. And so I wanted to warn them, but I didn't have an answer. So in order to make it more known, I changed the configuration file. And the first time I got it right, I added a comment in the configuration file, and I sent a mail. I told them, look, I changed your configuration file, here's the proof, look at them. Still no answer. And I did something else, like I wanted to add a bigger comment or something, and this time I failed. And by failing, I made the configuration file empty. And by making the configuration file empty, mycgiserver.com was not running anything on the scripts. So the scripts were just served as they were in a raw version, which means that instead of having the result of the script, you had the content, the source of the script, because they were JSP. And so you had all the passwords of all the databases that you wanted to. And it was a long time ago, but it was. I felt guilty, and at the same time, it was quite fun to do. Am I late? Yeah, you're a bit late. Sorry. But thanks for coming anyway. I implemented those two things, StoryMaster, basically. And the result is something that you can look here. Basically, I have two threads, which are sleeping and waking each other sequentially, and reporting progress depending on the counter. And it works. Just for you. Yeah, maybe not. I'm exhausted. I was sleeping at work earlier. That's not GitHub. Okay. Okay. Wayback Machine. Unfortunately, I'm lazy, I don't care that much. But if I really need it, yeah, I think about that. So the name is Wayback Machine. Okay. Let me check. Chat again. Oh, by the way, yeah, Jenkins compiled. Success, I'm happy. So yeah, after Java, I went to C, and at school I did some C++, which was a subset of the MATLAB matrix language. So basically, yeah, matrices of rational numbers and operations like inversing, transposing, augmenting, and of course, well, the dot, the scalar product, and addition, variables. So parsing a language, that was interesting. And what I really liked in that code, if I still have it, I think it was NTX. Let me check. I'll take a look quickly. Oh, it's not here. Oh, okay, okay, I see. Alright. So I don't think it built, so maybe it does. Maybe yeah, no, I didn't update it. Well, actually, I don't have read line. Let's see if it builds. I don't have a GitHub page for it. I might set one up. When I have some more stuff done, I will put up the first rest I did for x86 round. Okay, this weekend really. Reset to check all emitter comments. Aha! One thing I really like about open source, just publishing your work in general, is that because it makes it open and visible by anyone, pretty much the definition of public, you are in a different state of mind when you're coding it, because you expect people to see it, to look at it. So it tends to improve quality by some noticeable margin implicitly. Use it all the time in physics data analysis. LabPack. What's LabPack? Okay, that's super slow. Okay, seems to build. So that's very old stuff I wrote, yeah, 2005. Barely maintained in 2006. Oh, hey. Do I have list, for example? I think I have. Oh, I also had Doxygen documentation, but that's really crap. So, yeah. No, it's not here. It's probably in the main header. Yeah, that's unreadable. Well, not unreadable, but not great. I don't think the Doxygen generation works. And I don't think I have online help. Okay, this should be enough. Create a matrix. So M, for example, 1, 2, 3, 4. Okay, so N, A. Okay. This kind of stuff. Is that inv? What is it? Inverse. I write det, but not inv or inv. So what I really linear algebra pack. Okay, it's a matrix library. So wait. Is that what I think it is? 25 years ago, that could be it. Fortran. That's probably not it. I know Eigen. C++ mostly. This one is the one we use at work, I think. Well, one of the libraries we use. I use Python, obviously. It's one of the most important libraries in science. Yeah, but it's not the only one. In C, most notably, I remember some, like the GNU Scientific Library, Precision Library. But I remember one specifically that was really that even did code generation. I don't remember which one though. But what I really liked in C++ at the time, although I really don't like C++ now, is that, for example, the algorithm to compute the inverse or the decomposition, I think, matched the pseudocode like very closely. See, you can really write your object and you use an overloaded operator that makes it look like an element in a matrix, and actually you are invoking operators that have been overloaded. And this way I could really use the formulas that I have and apply them blindly. In C it would be functions everywhere. Yeah, like this, for example. But it's, like I said, it's very old code, it's the GNU coding style, but I really don't use anymore. So. But it was a nice project with, language, expressions, and so variable management, L values, etc. It was fun. Mostly because it's free, there's alternatives which cost a lot of money. Yeah. Except C++ does a very bad job with brackets overloading. Really? How so? How is that different? Operator and function overloading are two things that C should really implement. I disagree. I completely disagree. Possibly without the annoying name mangling. So that's one thing. You can't. You can't avoid name mangling. And the other thing is that personally I really don't like overloading as a concept, because it's implicit. You don't exactly know which overloaded version you're gonna invoke. It creates possibilities for ambiguities, and honestly it's just annoying. Having different names is just simpler. You can't overload multi-level brackets, you have to return to approach. Yes, that's right. But so let's take a look at how I did it, because I don't think it's very different now. So matrix in the header. Yeah, I return a pointer. So if I return a pointer, is this actually created? No, it returns a pointer to the content of the matrix. Rationals being a member, not correctly named. We don't see that it's a member, but it's a member, which means that I provide a pointer into the matrix content, which means that there is no temporary object. The temporary object is a pointer, so it's very efficient actually. can't overload xy equals z. I'm pretty sure you can. Why couldn't you just return an object that can be used as an L value? But you can make it not annoying. Func sucks. Void func int is cool. Oh yeah, I see what you mean. Okay. You're just lucky. What do you mean I'm lucky? Am I lucky? Anyway, C++ is not the most interesting thing. I'm curious about why I'm lucky. Your internal data matches the operator interface. Yeah, but it's a conscious design decision. Like, I understand what you mean. I understand that sometimes it's just not possible. I agree. But it's the same thing in C, and yes, if you'd wanted a specific, like if you wanted an efficient access to a matrix element, or let's just call it a matrix because we want double brackets, right? Then you wouldn't be able to use the operator and you'd have to use a specialized function. I agree. But if your matrix was represented in row image order, yeah, you're right. But I made it so precisely because so I consider one rule that I have, so let me show you. It's gonna take a little detour. So it's in the style, I suppose, the art of Unix programming, and then we have the basics of the Unix philosophy. And there is this rule that I often mention, the rule of least surprise. In interface design, always do the least surprising thing. So when I overload operators, I consider that because of this rule, the operator must do the same thing that it's expected to do. So if you use a plus sign, plus operator, it must add. If you use brackets, they must refer to like arrayed values. It doesn't make sense for me to overload operators such as C in and C out, for example. To overload bitwise operators to do something else. For me, it really doesn't make sense. I would never have done that if I designed the language, because it's surprising. So I understand that you can get used to it, etc., and why not? But for me, this is a very surprising kind of rule. So I overloaded the operator precisely because I implement a matrix. And because I implement a matrix, it makes a lot of sense to use array indexing. And that's why the operator interface matches what I want to do with it. Because the operator does what it's expected to do. So that's why it's possible. For the same reason, stdmap operator modifies the map even if it's used as an error value. It modifies the map. So I have no idea, well, I have some ideas, but I would assume that an std map would be a red-black tree, or a hash table, but I suppose that we have std hash maybe for that, so I would assume that it's a red-black tree internally, but we can't assume the implementation. How and why would the operator modify the map? I mean, if it's a red-black tree, the key has to remain the same. So the index must remain the same if it's indexed by such a key. Creates a zero entry in the map. Oh. why doesn't it raise an exception instead? That's surprising. That's very surprising. I would assume that if you look up something in a container and that thing doesn't exist, you get an error, an exception. Not a placeholder created implicitly. That's very surprising. Let's actually check that. Oh, I suppose it inherits some kind of interface. Usually implemented as red vectors, okay. Compare concept, yeah. And functions, okay. Okay. Return a reference to the value that is mapped to a key equivalent to a key, performing an insertion if such a key does not already exist. So, is that because the implementation doesn't know that you're reading it instead of writing into it? You can't index a const map for that reason. Yeah, okay, I see what you mean. It doesn't look like this. Is non-const because it inserts the key if it doesn't exist, if this behavior is undesirable, or if the container is const, at may be used. So yeah, see? At. That's what I would have used. That makes much more sense than operator overloading. If your object is not an array, like if its interface really doesn't match an array, and sorry, a red-black tree doesn't match an array because an array can remain read-only when you access elements, especially when you remove elements, for example. Well, not the array itself, but the other elements may not change. But obviously, if you use a tree, and not a trie, but really a tree that is based on comparisons, well, the tree might be rotated at some points, and you might need to change your other elements. So yeah, it's just not like an array. So if it's not like an array, why would we want to use an array indexing operator on it? That makes no sense to me. So that's why I consider operator overloading to be a bad choice, really, a bad language design choice. It's just an easy door to confusion and ambiguity and all the problems that may arise because of that. For me, accessing a dictionary with that syntax makes sense. It does, but in a very high-level language, like in Python, for example. And even in Python, its list dictionaries use a different operator, because dictionaries require objects to be hashable instead of comparable, for example. So that very critical design decision has a lot of impact on the rest of the language. And they thought about it, apparently. But in C++, especially in C++, which is still a low-level language, actually, yeah, it tries to be high-level, and it's not. It spans from very low, like quite low level to very high level, unsuccessfully. I agree. That's why I think that in such a context, with such requirements, operator overloading is a bad thing to have. And for me personally, overloading in general. I can understand why some people like overloading, and in a language like Python where the type is weak, why not? But if you have strong typing, and you might easily end up with overloaded functions that the compiler cannot choose explicitly, that automatically. If you have ambiguity between functions and the compiler doesn't know which one to choose because you have multiples that may match, well, normally it's not a problem because semantically it should be the same thing. So, for example, you went from a constant char pointer to a string to whatever type you have in your overloaded functional method. But if it's not the case, and sometimes it's not, and even if it is, if you have a bug, you don't even know which code to look. Like you have to debug it with some low-level tools like a debugger. When used properly, operator overloading just make programming more comfortable. I know why you say that, especially if you do a lot of math, algebra, vector math. I understand that, and that's why I like Python, because in Python, for that kind of thing, weak typing is actually a good design choice. From my point of view, like that's what I think. That's an opinion. You really have objects that might be really anything from scalars to matrices, vectors, whatever. I agree with you that in math, especially, it makes a lot of sense. And that's probably why Python is used so much for math stuff in general. But again, because of the strong typing, the problem is not really overloading in itself. The problem is mixing overloading with strong typing, and so ending up with multiple possible paths that should do the same thing with different implementations. And that's something I really don't like, because you lose control over what's done, and it makes debugging harder, and it makes understanding your code harder. You don't know. So usually what happens is that the compiler will force you to choose one version by explicitly casting your operator. But if you have to explicitly cast it, why do you want to overload it? Like, just have different names and don't cast, and it works. Yeah, but I like C because Python is not as fast when I program simulation with a billion elements moving. Yeah, but then what I would do is that I would program this particular algorithmically expensive operation in C, and I would bind it to Python. There are better choices than no typing at all for that. I'm not saying no typing, I'm saying weak typing. I'm waiting for JIA once the compiler is out and try. Hopefully it has everything good that C has and much more. JIA. Is that a language? Okay. Isn't there a Python version that compiles to C? Maybe Iron Python or something like that? Maybe. I know about PyPy, but it's only for Python 2. A lot of numerical Python is C in background anyway, yeah, like NumPy, for example, is a lot of C code. Compiler is still being developed. Okay. But everything good that C has, yeah, I'd have that, unfortunately. Because, at least from my point of view, a lot of good things that C has are perceived as defects by many people, especially people who come from higher level languages. Like, like accessing outside array bounds and even using negative indexes is something I really like, and many people consider that like a heresy or something. So if the language has that kind of thing, I would think that it has at least one good thing that C has, but I doubt it. Blue really likes C and is a competent programmer in my opinion, so I think he knows what he's doing. Maybe. Like, can you give me a link of his code? You made me curious. But Medusic, it's really, it's really a cultural difference, I think, about overloading. Again, I don't mind typing a little more to remove a lot of problems. I don't think you can find his code anywhere. He's not really into open source. He's the developer of the Witness and Braid. Yeah, okay, but that sucks. He streams on Twitch, so maybe I can just have a video where he codes and look at what he does. Like, wouldn't he be the developer I watched who talks about volatile in multithreading? Was that him? Yeah, sure, why not? I'll look it when I have time. Which should be okay because it's a weekend, Oh, thanks. No, that's not him.
Better how to construct them, destruct them, and copy construct what the new version is, and it's a relatively small change to the code. Much smaller than this giant nightmare that I had over here, right? And you sort of know that there aren't going to be bugs with this. Now, because code started, again, I claim in my really apply to the function. The argument type for the person who takes the function as an argument has to be totally different. You probably have to use this standard function phrase.
Yeah, I'd like to have some code, I don't really see code here. Julia is also on the horizon. Don't know how late it is already, but some people seem to like it. I've heard of it too. Why do I need to type more for dictionary access? It is absolutely unambiguous. I will assume unambiguous. Again, because like it's about the type. So if you ask the question alone, it makes no sense, right? Because obviously, like you say, it's unambiguous. But if you are in a language where typing is strong, then it's going to be ambiguous. And actually, the operator overloading may not be ambiguous. I'm really talking about function overloading in general. So what is this one? Without the W, yeah.
So that would be nice.
Ah.
Down here in the bottom, commented out is sort of what the original.
That's the same thing, right? Ninja me, okay, yeah, I see. I really like to see the code, but really not just 3 lines that are used to demonstrate some principle, but really a couple of functions that solve like a practical problem. But you won't change my mind, Medusic, on this. Operator overloading is close to having method with the same name in 2 different classes, not 2 global functions with the same name. Oh wait, I'm gonna reread that again. Operator overloading is close to having method with the same name in 2 different classes. I don't understand that. What 2 different classes? Not 2 global functions with the same name. Yeah, okay. I'm not talking about 2 global functions with the same name. We could have two methods of the same class with different names, or the same name. I don't understand what you mean, because for me, operator overloading is really like having, 2 methods with the same name for the same class. I really consider operator to be methods. little bit old, so they're going to be outdated. Okay. But the reason you won't change my mind is because, again, it's about culture, and the reason why I say I don't mind writing a bit more to avoid confusion, ambiguity, and all these problems is not about operator overloading itself. It's really when you have different arguments. It's really about the type, because how the compiler chooses which version to use entirely depends on the types. Yes, and there is only one operator for STD map. Yes, but... Okay, I see what you mean. But here, again, it's not the same reason. So, when you have arguments with different types, this causes potential ambiguity. So that's the reason why I don't like function overloading in general. Now, for operator overloading, what I don't like with it is that it must, like I said, it must match the precise semantics of whatever it overloads. Okay? So here, that operator is array indexing. And array indexing has actually a lot of, well, quite a few implicit constraints. Like you said, one of them being that you can't change anything else than what you're accessing. And because an STD map is not an array, this assumption changes. So it's not about ambiguity, it's about the real semantics of the operator, which is not the same, which is surprising. Right? It's surprising that accessing an element changes the others, some others. You don't know which ones, because it's a red-black tree internally. So what you need to understand is that an interface always has two sides. You have the user side, which looks the same, and indeed it could be said that it's the same, and then you have the implementation side. And if the implementation side doesn't match all the criteria of this, all the semantics of the interface, well, the interface is wrong, it gets surprising. And because of that rule of least surprise that I mentioned, I consider that overloading that specific operator is a mistake. It's not the same. Yeah, and I precisely mentioned C-in and C-out, and I explicitly, well, I mean, I said it clearly that I consider those bitwise operators used for input-output to be a stupid mistake. Something that if I designed C++, I would never have done it that way. Precisely because they're surprising. You're using bitwise operators for something that is absolutely not bitwise operations. So that's a rule I force myself to follow. Some other people don't have a problem apparently with causing surprises, and again, it's going to be surprising at the beginning, and once you get used to it, it's not surprising anymore, so why not? But in this case, it's actually, this case is interesting because the difference is so big between bitwise operators and input-output on IOStreams objects that it's almost okay, in the sense that confusion is very unlikely once you get used to it, which is quick. Whereas for the STD map case, the operator is almost the same, like almost the same, but not exactly. And because of that tiny difference, you get this surprising behavior. So I'm going to refer to that rule again. Pay attention to expected audience, yeah, okay. The flip side is to avoid making things superficially similar, but really a little bit different. This is extremely treacherous because the seeming familiarity raises false expectations. It's often better to make things distinctly different. Exactly. So that's really the different than to make them almost the same. So actually, the case of the STD map overload is much worse than the IOStream one. What's wrong with DSL? If it simplifies coding, DSL. What's DSL? if it simplifies coding. So again, I have this rule, which I state here, but is implicit in the art of Unix programming, which is explicit programming. Make your code state what it does. Domain specific language. What's a domain? I would assume that here IOStream would be the domain. If it simplifies coding. Well, I don't think it simplifies coding. That's the problem. I think at first, from a naive point of view, it may look the same, it may look like smaller, it may look easier to use, but the big picture is that every time you use something that differs between domain, you have an additional variable, which is the domain, and which is implicit. So it adds an implicit variable to your combinations. So it's doubly wrong, because you add a variable, and in addition to that, it's implicit. So you may easily forget about it because of that. And that's why I emphasize the word explicit here. That's why I don't like inheritance, for example. Because if you don't know that it's there, it's difficult to understand to have the big picture in mind. And if you don't have the big picture in mind, you're going to end up with cases that you really don't want. Like the classic example is the banana, the gorilla, and the jungle. You know, you have to pull everything. And other examples include the explosion of algorithmic complexity. It's explicitly stated in the documentation. Well, that argument amounts to say that C++ is entirely specified, and when you code, you should have the complete specification in mind. And if you write bad code, it's because you forgot one tiny line among the other thousands, and it's your fault because it's explicitly stated in the documentation. Needless to say, that's an argument I can't accept. I try, like, one of the objects of my streams is to show how to master complexity. How do you master complexity? You break it down into simple things that you can think about. You can't think about the entire specification of a very complicated language. So again, if you break that down into domains, instead of simplifying, you actually multiply the number of cases. So you increase complexity. That's against what I'm trying to do. Removing overloading, so not having overloading in the first place actually, means that yes, you're going to have to choose the function yourself. The compiler is not going to do that for you. But it's not that difficult. It's actually it's very easy. It's a little bit annoying, but it's very easy in practice. And the risk of error and the time you're going to spend debugging the fucking thing will be non-existent. Just for that simple problem, right? Just for the overloading problem, because you'll just have to choose the right function name. That's what the problem is. It's very simple. I agree that there are many errors in C++ design, yet I don't see anything wrong with overloading syntax for a specific domain. Well, like I said, you have one thing per domain, so if the domain is not explicit, it makes an additional implicit variable, and usually that's the case. And again, it's the case because you have a surprising behavior, a small subtlety that may not be in your mind, because your mind is probably busy with other things that are more important, like the problem you're trying to solve, and not the language itself. And so, again, how do you measure the complexity of a function usually? Not really by its size, but by the number of variables that combine. So, I can't accept an argument that says that adding a variable that combines and that may be implicit is a good thing to do. That's just my argument. But again, it's an opinion, it's a lot of culture and tradition, it's not exact science, it's craft and experience mostly, so, you know. For DSL for UI animations, I don't want to imagine what it would look like without a prior overloading. So that's what language is that, by the way? DSL, okay. DSL for UI animations. But this is object-oriented, right? Like, set is a method. What is alpha? What is this thing? Foreground? Column? What is the column? Oh, it's Lua, okay. Yeah, I don't know Lua. I should learn Lua one day. Like, I had a good excuse with World of Warcraft. I never bothered writing a signal plugin. Well, extension? Add-on? Yeah, add-on. So I don't know what the code does here. It's syntactic sugar for foreground, alpha foreground. Okay, I see. So yeah, it's basically that's weird though, because if it's a method, why doesn't it have the object on which it is invoked as the first argument, as this, for example? It doesn't have bound methods, so it emulates methods with. Okay, I see. Okay. I don't have enough experience. Well, I don't have any experience with Lua, and the code I see here is like I don't know what it does, so I can't really point out to something specific that I may use as an argument not to overload operators, well, methods here. And when you say that you can't imagine what it would look like without overloading, well, maybe you can't, but maybe with time I could come up with something that looked decent. Who knows? Plus are overloaded, runs both parts in sequence, plus runs them as parallel. I see. But here it makes sense. See? Actually, one thing I like I said, I'm not entirely against operator overloading, as long as they exactly match what the native operators do. Like, exactly. So that's important. If you do it in parallel and it's exactly the same as if it was done sequentially, in terms of semantics, for example, that you can't, you prevent the programs from seeing any transient state, so that it looks like it was done sequentially, for example, then it's fine. If you don't have the same, you know, the kind of details that you mentioned about STD map, for example, that's probably fine. And like I said, I showed my matrix, my little matrix program, as an example of operator overloading that actually enabled me to write the code in a way that looked like what I have in the book, which is great. I understand that, but for me that's a very specific use case of overloading. It's operators first, so the name, like, there isn't really a choice of name. You can't change the name of plus, for example. It has to be plus. So the only thing that may change again is the type. And here, yeah, the type may change, I agree. If you're careful and you make sure that you have no ambiguity, why not? And if the resulting code looks like code, like regular code that would use these operators, and they do act exactly without ambiguity, without little detail differences, then I'm okay with it. But I consider that to be really an exception in a bigger set of anti-patterns. So native dot is a string concatenation, timescale is a piece of animations, and are combined to complex sequences with concatenation and plus. So yeah, concatenation and running in parallel. Okay. Yeah, so here plus means running in parallel, and okay, so yeah, I see what you mean, and I would definitely not use operator overloading for that. Definitely not. Absolutely not. But like you said, here it's not even a domain-specific. Well, it is a domain-specific language. Yeah. This really means that it puts a burden on the developer to always keep that in mind. So if it's okay, like if you consider that as an extension of the language, like you said, a domain-specific language, but more than that, for me it's extended because you have a base, which is LUA. You extend it by removing the native dot and plus operators and replacing them with something else. And so the person looking at the code has to keep that in mind all the time. So you increase the burden of the language. And I don't really see the benefit, honestly, compared to something that was more explicit and a bit longer. Our artist who doesn't know anything about programming edits it, no problem. Okay. Like you said, he's an artist that doesn't know anything about programming, so he doesn't have all the details in mind. He's limited to something that is simple. He would not be my target audience, and he doesn't even know what functions are. Yeah. If it works for you, that's good. Okay, the end result is really pragmatic. If it works for you, that's good. But in my experience, that's not how it's going. So again, I saw just a small snippet of code that you showed me, and I trust you when you say that. I don't think you're lying. My experience is quite the opposite, really the opposite. That people, the people I've worked with, made lots of mistakes because of that. Couldn't understand compiler errors or debugger states, like what the debugger would tell them. And I know it because because when they had problems that they couldn't solve after a week, I was the one who people would fetch to take a look at. So that's how I got to see a lot of horror stories in other completely unrelated departments. But if it works for you, I mean, that's the ultimate argument, it works, right? To say that something is better using that kind of argument means that you would have something strictly equivalent but different that you can compare, and that you would have lots of statistics about it. That's completely unrealistic to think about, which means that I can't say that my way is better than your way or anything else, So ultimately, if it works for you, that's good. But from experience and from the tradition, culture, experience, etc. that I have personally, that's not how I would have done it. That's all. Just want to show you another part. Sorry. Now, I'd like to end the stream. I'm going to make Lori Master right. Are people still awake, by the way? Sleepy Panda Bear. Okay, this one is asleep, definitely. Hello, by the way. Okay. So you wanted to show me another power, so yeah, sure. Free to go. Okay. No, I'm gonna end here. So, thanks a lot for the chat and for the argument. Because even if we disagree, it's perfectly okay to disagree. Like I said, what I think is that ultimately what matters is that it works. As long as it's not too expensive, as long as it's maintainable over time, that's okay. I'm just saying it's not always that bad. Yeah, okay. I'm not saying it as a rule, like it's not dogma. I regularly say that coding is a lot more about something that we can't consider to be hard science, like languages, so linguistics, it's much more a craft and about creativity than engineering. And by the way, there is a debate about what we call software engineering. Controversy, if you're interested in that. Poor analogies for what they call the radical novelty of computer science. Yeah. So, because it's about things that are not really science, it's very difficult to know who's right. And as long as it works, that's okay. Coding is about hacks. Yeah, you could say that. When's next appointment? You gotta make the stream thing happen more often. Twice a week is not enough. Yeah, no, not right now. Sorry about that. I'm not currently in a state of mind where I want to code like I did, basically this year from January to September and the beginning of October, but really at the end of September, I was coding all the time, like at work, after work, during the weekends, even when I went way away to rest, for example. Like I was coding on a boat, for example. And since October, it's been no. My body just doesn't want me to code anymore. You know, my brain, the unconscious part of the brain, like the limbic system and everything, that basically drives what you want, doesn't want me to code anymore. So I'm not coding. I'm still coding this though because it's fun. It's probably interesting to more people because it's more accessible, and I also do it usually. I do it with Metal Snake, so it's also nice to have someone to talk to directly. We don't have to code; we can just have a chat. Yeah. Let's be a little more productive, you know. I mean, it's fun, and I really like having this kind of chat. But twice a week I think is a good pace for that. And you know, you can just come in earlier if you want to chat more. Alright, guys. The music is actually quite good, but I'm gonna put this one, For the Love of God, which is really great. So let's raise the volume a little, like this. And thanks for watching, enjoy the music, enjoy your weekend, enjoy life, be lucky, etc., etc.
walking the fine line between pagan and Christian.